Around a young star, a disk of dust and fire slowly begins to organize. What will follow is one of the most violent and creative chapters in planetary history. This is how Earth was born. About 4.6 billion years ago, the early solar system was a chaotic place, filled with debris left over from the Sun's formation. According to NASA's solar system formation models, this cosmic dust wasn't just floating aimlessly. Microscopic grains, no bigger than particles of smoke, collided and bonded through electrostatic forces, much like static cling on a dry day. It was a quiet, almost imperceptible beginning. Over millions of years, these tiny particles grew. They clumped together, forming pebbles, tin boulders, and eventually kilometer-sized bodies we call planetesimals. Think of them as the building blocks of planets. At this point, a more powerful force took over: gravity. The larger planetesimals began to exert a gravitational pull on smaller ones, attracting them into their orbit. This triggered a chain reaction of collisions, a process known as computer simulations conducted by NASA's Jet Propulsion Laboratory allow us to visualize this cosmic construction site. They show that Earth formed through thousands of high-energy impacts. Each collision released an immense amount of heat, enough to melt rock. The early Earth was not a solid, tranquil world. It was a molten, glowing sphere, constantly growing, constantly evolving with every violent impact. It was a planet being forged in fire. As our young planet grew hotter and larger, it entered a critical phase of global melting. Imagine a world covered in a planet-wide ocean of magma. According to studies published in Nature Geoscience, this extreme heat allowed the materials making up Earth to separate based on their density. The heaviest elements, primarily iron and nickel, sank under their own weight, migrating toward the center. Lighter materials, like silicate minerals, rose to the surface like oil on water. This process, known as planetary differentiation, is responsible for creating Earth's layered structure, a fundamental feature of our world. The dense iron and nickel formed a superheated core. The lighter silicates cooled to form the vast, semi-molten mantle and, eventually, a thin, solid crust. This internal structure isn't just a theory. It's confirmed by seismic data, studied by NASA and international space agencies. The way earthquake waves travel through the planet tells us precisely what lies beneath our feet. But how do we know when all this happened? Scientists use a technique called radiometric dating on meteorites' pristine leftovers from the early solar system. By measuring the decay of radioactive isotopes within them, we can pinpoint the age of our solar system and, by extension, our planet. Multiple studies, published in prestigious journals like Nature, converge on a consistent age for Earth: approximately 4.54 billion years old. Just as the young Earth was settling into its new form, one final, cataclysmic event would forever shape its destiny. According to the giant impact hypothesis, a theory strongly supported by research from NASA, the European Space Agency, and numerous publications, our planet was not alone. A Mars-sized body, which scientists have named Theia, was on a collision course with Earth. The impact was unimaginable. Theia struck Earth with such force that it vaporized colossal amounts of rock from both bodies, ejecting a massive cloud of superheated material into orbit around the wounded planet. Over time, gravity went to work on this ring of debris. The particles began to clump together, accreting into a single, large sphere. This is how our moon was born. The evidence for this incredible event is compelling. Lunar rock samples, returned to Earth by NASA's Apollo missions, reveal an astonishing secret. Their isotopic compositions, a kind of chemical fingerprint, are nearly identical to the rocks found in Earth's mantle. This isotopic crisis is a key piece of evidence supporting the idea that the moon was formed from Earth's own material. The collision also had other profound effects. It knocked our planet off kilter, giving Earth its axial tilt, the very reason we have seasons. And the moon's gravitational pull has acted as a stabilizer ever since, preventing our planet from wobbling chaotically, which has been crucial for a stable, long-term climate. As the relentless bombardment from space debris slowed, Earth finally began to cool. Its molten surface started to solidify, forming the first crust. But the planet was still incredibly active. Volcanoes erupted across the globe, releasing gases that had been trapped within the planet's interior. This outgassing formed Earth's first true atmosphere. According to the NASA Earth Science Division, this primordial air was toxic and alien, dominated by carbon dioxide, nitrogen, and vast quantities of water vapor, with virtually no oxygen. As Earth continued to radiate its primordial heat into space, global temperatures dropped below the boiling point of water. The water vapor that had filled the atmosphere for millions of years began to condense, forming thick, planet-shrouding clouds. And then it began to rain. It wasn't a brief shower, it was a torrential downpour that lasted for centuries, flooding the newly formed basins and craters. Geological evidence cited in Nature shows that liquid water existed on Earth's surface as early as 4.3 billion years ago. While volcanism provided much of this water, some may have also been delivered from space. Isotope studies from the European Space Agency's Rosetta mission, which analyzed suggest that carbon-rich asteroids were also a significant source, carrying frozen water to the inner solar system and delivering it to our thirsty young world. By about 3.8 billion years ago, the chaos had subsided. The Earth had transformed. It was now a water world, a blue marble with stable oceans, active geology, and a steady supply of energy from the young sun. The stage was set for the next, and perhaps most extraordinary, chapter in its story. Research published in Nature indicates that the oldest known signs of life, found in ancient rocks as isotopic signatures and fossilized microbial structures, date back to this very period. According to NASA's astrobiology program, the conditions were just right. The unique combination of liquid water, a rich diversity of chemical elements, and the long-term environmental stability provided by its size and its moon allowed life to emerge from non-life. From the fiery remnants of ancient stars and the violent collisions of cosmic debris, a living world was born. The Earth was shaped by gravity, fire, and time. Its story is written in rock, in light, and in life itself, and it remains one of the universe's most remarkable creations.